Hello mathematicians, in this video we are going to look at rational functions and I want to show you a couple of little tricks for making your life much easier for these things. I'm going to do the one on the left first, then I suggest you pause, try the one on the right and see how you go, then I'll describe it as well. So first off, finding the asymptotes. Now we just have to remember that when we've got a function like this, we're not allowed to divide by 0. So one of the asymptotes is obviously the case when x minus 3 equals 0, so x equals 3 is the first asymptote. The other asymptote is a bit more confusing. We know, by the way, in general, that this graph is going, it's based on the graph of 1 over x, which has an asymptote there at x equals 0, and another one at y equals 0. We know the graph is doing something like this. And so we know that as x is getting larger and larger, the value of y is approaching some limit. For the case here where y equals 1 over x, as x gets larger and larger, y gets closer and closer to 0 because we've got one thing being divided by an increasingly large number. And we can kind of use that logic here to, I'm going to say, fudge one of the asymptotes. So we have question 1 here. So second part of question 1, we've got the dodgy method. The dodgy method is to say as x approaches infinity, then what we've got, f of x, is really approaching 3 lots of infinity divided by infinity. Now, this is horrible math, absolutely terrible, but it's probably going to work most of the time. What we're saying is if you've got, like, let's say x was a billion and you had 3 billion plus 2, well, that's pretty much just the same as 3 billion. We don't really care about the plus 2. And likewise on the bottom, if x is a billion and we're taking away 3, that minus 3 makes almost no difference whatsoever. So we can say that this is approaching 3. So our other asymptote is going to be y equals 3. Now, yes, that's not very nice at all. Let's do something better. And we are often asked to express this thing in the form, let's say, um, a plus b over x minus 3, something like that. And the way we're going to do that, we don't need to do any kind of long division. We're just going to do a little bit of a hack. And we're going to say that 3x plus 2 over x minus 3, we're going to express the top as the multiple of the bottom. So I'm going to start with this. I know at the moment this isn't correct, but we're going to sort of do test and adjust. We're going to try something and then adjust it to make it right. Now, at the moment, if I expand that bracket, I get 3x, which is what I wanted. I've got the 3x on the right, which gives me the 3x on the left. But the problem is that when I expand it, I also get minus 9. When I do 3 times minus 3, I get minus 9. And I don't want minus 9, I want plus 2. So to fix that, I need to add 11. Okay, and we might think to ourselves, well, what's the point of that? Because now I can split that fraction. I probably wouldn't write this line if I was doing it for real, but just to show you what's going on, we know that we can split fractions according to the numerator. And now we just have 3 plus 11 over x minus 3. So this is y equals that. So we end up with y equals 3 plus 11 over x minus 3. So that's something you might be asked to find in any case. And now we can apply the same logic. As x here gets larger and larger, we've got 11 divided by a very, very large number. So this whole thing approaches 0. And so we're left with the asymptote y equals 3. So because we're going to plot this, sketch the graph rather, we can start to put these things in the diagram up here. So we've got our graph with an asymptote y equals 3. Make sure we label these y equals 3, not y is not equal to 3. It's tempting sometimes. Oh, and x equals 3 as well. It's not very imaginative, but that's the way it goes. X equals 3. Now we're going to find our axial intercept. And this is so forgettable, but so important. On the y-intercept, the y-axis, it is always the case that x equals 0. Let's just shift this up slightly. So if x equals 0, we know that y equals, well, we've got 3 lots of 0 plus 2 over 0 minus 3 equals minus 2/3. I would suggest you write these out as a pair of coordinates as soon as you've done them. Otherwise, you'll make a silly mistake, potentially. The x-intercept, it's slightly harder. For every single x-intercept that ever there was, y equals 0. So we need to solve 3x plus 2 over x minus 3 equals 0. Well, for this to be the case, we need the numerator of this fraction to equal 0. So we need 3x plus 2 to equal 0, x equals minus 2/3. Oh my goodness, how have I managed to choose such a tediously symmetrical function? Minus 2/3, 0. So we can pop that up here. Now we were sketching the graph and we can see our values. We had 0, minus 2, so no, 0, minus 2/3 on the y. Oh yes, minus 2/3, 0 on the x. I would say just as a motor skill thing, don't plot the points, so we know that's roughly where they are. But draw the graph first and then decide where the points are. We're going to try and get that just right. We don't want it to be going away from the asymptote. We don't want it to be missing the asymptote completely either. So we label them properly. Minus, sorry, no, 0, minus 2/3 for this one, and here minus 2/3, 0. And we know that with these hyperbolae, once we found one of the things, we know the other one is going to be diagonally opposite. So we get to the graph. And in fact, we have described the behavior as x approaches infinity as well. We can say that as x approaches plus or minus infinity, y approaches 3. So let's just quickly review what we did. First off, the asymptote. There's the obvious asymptote. Whatever will make the bottom equal 0 is our x asymptote. The y asymptote, we've talked about the dodgy way of looking at it, considering what happens when x gets super large, what numbers can we ignore? We've got a better way of rearranging the equation, which I think you should definitely practice on the next one, so we can write it in a way where we don't have an improper algebraic fraction. Because incidentally, an algebraic fraction is considered improper if the order of the top is the same or greater as the order of the bottom, the order being the highest degree of x. So we've got a linear over a linear, order 1 divided by order 1. So that would be improper. If we had a quadratic on a linear, that would be improper. A linear on a quadratic, that would be okay. We found this way of rearranging it to find the y asymptote. We described the behavior as x approaches plus or minus infinity, and we sketched the graph. That's what this was all about. So pause the video. The second one has a little bit of a twist in it. Let's see how you go. Okay, hopefully you paused. The x asymptote, fairly straightforward. 4 minus x equals 0, x equals 4. That's our first one. The dodgy way of doing this is we've got 2 times infinity over negative infinity, so we're going to have negative 2 as our y asymptote. But let's do this properly. Let's say if y equals 2x plus 1 over 4 minus x. I know I want 2x, so I'm going to go minus 2 4 minus x. So I've got to make sure that when I expand this, I do get my 2x. And that's what this gives me. Minus 2 times minus x is 2x. It also gives me minus 8. I don't want the minus 8. I want plus 1. So I need to add 9. This is then divided by 4 minus x. And I wouldn't do that trick most of the time. I would go minus 2 plus 9 over 4 minus x. Sorry, by trick, I meant intermediate step of working. Oh, brain dropped out for a minute. And so again, we can see here, as x approaches infinity, this bit will approach 0, and so we have our other asymptote, y equals negative 2. So we would probably write something as x approaches plus or minus infinity, y approaches negative 2. So asymptote y equals negative 2. Now we find our intercept. The x-intercept is always the case when y equals 0. 2x plus 1 over 4 minus x equals 0, which means 2x plus 1 equals 0, x equals minus a half. Because we know for a fraction to equal 0 like this, we know the top needs to equal 0. We can't have a case where top and the bottom equals 0, but that won't usually come up. Next, we have our y-intercept when x equals 0. Probably would have done this one first. It's slightly easier. So y equals 0 plus 1 over 4 minus 0 equals a quarter. And I should have said here minus a half, 0 for my x-intercept, and then 0, a quarter for my y-intercept. And now we can sketch this happy little thing. My graph. So we have a y-asymptote at y equals negative 2, x equals 4, and we can see that minus a half, 0 is going to be about there, and 0, a quarter is going to be about there. Again, don't feel you have to try and get these to any kind of scale. As long as we know that the graph is going to be crossing here, we can just make sure that we go through like that. And pretty much make sure that we haven't hit that asymptote. It's not the best curve in the world. And see, I probably want to make sure there was a bit more page there to draw on. Now we can plot the points. So we've got negative a half, 0, and 0, a quarter. And I mean, it's nice that the distance there, a half, is bigger than the distance of a quarter. And there we have it. That's how we plot rational functions.